Deep inside every black hole, our best physics says there lies a point where matter becomes infinitely dense and space-time tears apart completely. But what if this mathematical nightmare is actually impossible? What if the universe has secret safeguards that prevent these reality-breaking singularities from ever forming? We're about to journey through quantum firewalls that might replace black hole hearts, explore cosmic bounces that could have birthed our universe, and discover why the most brilliant minds in physics are now questioning everything we thought we knew about the most extreme objects in existence. If you're ready to have your mind blown by the possibility that singularities are just mathematical ghosts, hit that like button and subscribe for more reality-bending physics. Prepare yourselves. We dive deep. Music, picture a calculator trying to divide by zero and simply displaying error. That's essentially what happens when physicists try to describe the center of a black hole using Einstein's equations. The math doesn't just get complicated or difficult to solve. It literally breaks. The equations start spitting out infinities like a broken vending machine dropping endless candy bars. Here's the problem that has haunted physics for nearly a century. When matter collapses under its own gravity, Einstein's general relativity predicts it will keep crushing inward without limit. The density climbs higher and higher. First, atoms get squeezed closer together. Then, electrons crash into protons. Then even neutrons can't withstand the pressure. But the crushing doesn't stop there. According to the math, matter continues collapsing until it reaches infinite density at a single point with zero volume. Physicists call this nightmare scenario a singularity. It's like trying to squeeze the entire population of New York City into a space smaller than the period at the end of this sentence. Then keep squeezing. The curvature of space-time around this point also becomes infinite. Imagine rolling a bowling ball on a trampoline, watching it create a dip in the fabric. Now imagine that dip becomes so steep it forms a bottomless pit that tears the trampoline completely apart. That's what a singularity supposedly does to the fabric of reality itself. At this point, time stops making sense. Distance becomes meaningless. Every physical law we've ever discovered simply gives up and returns mathematical nonsense. It's as if nature itself throws its hands up in defeat and declares, "I can't compute this anymore." The truly unsettling part: our most trusted theories predict these mathematical monsters should be lurking at the heart of every black hole in the universe. That means millions of points where physics completely breaks down are scattered throughout space right now. Some black holes contain the crushed remains of stars 20 times more massive than our sun, all compressed into mathematical points smaller than a grain of sand. Even worse, cosmologists believe our entire universe emerged from a singularity during the Big Bang. According to this view, everything we see around us, from planets to galaxies to the very atoms in your body, somehow expanded from a point of infinite density and temperature. The math suggests that at the very beginning of time, physics was not just broken, but utterly meaningless. This creates what philosophers call a crisis of explanation. How can our most successful scientific theories predict their own destruction? How can mathematics that accurately describes everything from GPS satellites to gravitational waves suddenly produce answers that make no physical sense? It's like having a perfect map that guides you flawlessly through every city and countryside, only to discover that certain locations are marked with "here be dragons" and math stops working here. But what if the dragons are just figments of mathematical imagination? What if the real universe has built-in safeguards that prevent these reality-breaking points from ever actually forming? Einstein never wanted his theory to predict the destruction of physics itself. When he first developed general relativity in 1915, the equations were supposed to describe how massive objects bend the fabric of space-time. Stars, planets, even light beams would follow curved paths through this warped cosmic geometry. It was elegant mathematics that turned gravity from a mysterious force into the natural motion of objects through curved space. But mathematics has a way of revealing truths that even its creators never anticipated. Within just a few years, Other physicists began finding solutions to Einstein's equations that he found deeply disturbing. These solutions describe scenarios where matter could collapse so completely that it would disappear from the universe entirely, leaving behind regions where spacetime itself became infinitely curved. Einstein fought back against these predictions. He published papers attempting to prove that such extreme collapses could never actually happen in nature. He argued that quantum effects or the rotation of stars or some other physical mechanism would always prevent total gravitational collapse. He believed the universe must have natural limits that would stop matter from crushing itself out of existence. The problem is that Einstein's own equations disagree with him. General relativity contains no built-in stopping mechanism. Once enough matter gets concentrated in a small enough region, the mathematics demands that collapse will continue indefinitely. It's like trying to design a car with brakes, only to discover that your engineering equations predict the brakes will fail whenever you need them most. Here's what makes this situation so unsettling for physicists. General relativity has passed every experimental test we've thrown at it. The theory correctly predicted that massive objects would bend starlight, that time would run slower in strong gravitational fields, and that accelerating masses would create ripples in spacetime itself. When scientists detected gravitational waves from colliding black holes in 2015, they found the signals matched Einstein's predictions with incredible precision. So, we have a theory that works perfectly for describing everything from falling apples to orbiting planets to colliding galaxies. But this same theory also predicts that under extreme conditions, physics itself will break down completely. It's like having a car that runs flawlessly on every road except the ones where you need it most. The mathematical breakdown occurs because general relativity treats spacetime as a smooth, continuous fabric that can be curved without limit. Picture stretching a rubber sheet and placing increasingly heavy objects on it. The sheet will bend more and more. But in Einstein's mathematics, there's nothing to prevent it from being stretched into an infinitely deep pit. This creates what physicists call a geodesic incompleteness. Imagine you're following a perfectly straight path through curved spacetime, but suddenly your path just ends. Not because you hit a wall or boundary, but because the mathematics simply stops providing meaningful answers. Your journey through space and time reaches a point where the equations throw up their hands and declare, "We can't tell you what happens next." But perhaps the most brilliant mind of the 20th century was wrong about his own theory. Perhaps nature does have hidden safeguards that Einstein never discovered. Mechanisms that kick in precisely when his equations start producing infinities. Perhaps we're about to discover what really happens when matter tries to collapse beyond all limits. Step across the event horizon of a black hole, and according to Einstein's math, you're already dead. Not immediately dead, mind you. You might have hours or even days left, depending on the black hole's size. But from the moment you cross that invisible boundary, your fate becomes mathematically sealed. No force in the universe can prevent you from eventually reaching the singularity at the center, where you'll be crushed into a point of infinite density. This grim prediction has haunted physics for decades. The event horizon acts like a one-way membrane in spacetime. Light can enter but never escape. Matter can fall in but never climb back out. It's the ultimate point of no return, marking the boundary between the normal universe and a region where physics breaks down completely. But here's where the story gets interesting. What if crossing the event horizon doesn't actually doom you to encounter a singularity? What if something happens inside black holes that prevents the infinite crushing that Einstein's equations predict? Think of it like walking toward the edge of a cliff in thick fog. From a distance, it appears that anyone who steps over the edge will fall forever into an infinite abyss. But what if, hidden by the fog, there's actually solid ground just a few feet below the cliff edge? What if the seemingly endless fall is just an optical illusion created by limited visibility? Recent advances in quantum physics suggest that black hole interiors might contain similar hidden features. Instead of crushing matter into mathematical points, the extreme conditions inside might trigger quantum effects that hold the collapse before it reaches infinite density. The singularity might be like a mirage that disappears when you get close enough to examine it carefully. One possibility is that matter falling toward the center encounters what physicists call quantum pressure. Just as normal matter resists being compressed beyond a certain point, quantum effects might create an even stronger resistance that kicks in at incredibly high densities. Instead of collapsing to zero volume, matter might bounce back like an extremely rigid spring being compressed to its limit. Another intriguing idea suggests that the fabric of SpaceTime itself has a granular structure at the smallest scales. If space is made of discrete units rather than being perfectly smooth, then matter can only be compressed until it reaches the size of these fundamental space pixels. It's like trying to squeeze a beach ball into a container smaller than a single grain of sand. The balls simply can't fit into a space smaller than the basic building blocks of space itself. These quantum effects would completely change what happens inside black holes. Instead of a crushing singularity, you might find a bizarre quantum realm where normal concepts of time and space operate according to entirely different rules. Matter might exist in exotic states never seen anywhere else in the universe. Energy and information might swirl in patterns that our current physics can barely describe. The most mind-bending possibility is that black hole interiors might contain entire universes in their own right, with their own laws of physics and their own possibilities for complexity and structure. But to understand how this could work, we need to dive deeper into the quantum realm, where reality itself might be fundamentally different than we imagine. At the smallest scales of reality, matter refuses to be pinned down. Quantum mechanics tells us that particles don't have definite positions or velocities until we measure them. They exist in clouds of probabilities spread out across space, like ghostly possibilities waiting to become real. An electron orbiting an atom isn't following a specific path like a planet around the sun. Instead, it exists as a fuzzy probability cloud that somehow occupies multiple locations simultaneously. This quantum fuzziness might be exactly what saves the universe from singularities. When matter gets compressed to extreme densities, quantum effects become increasingly dominant. The normal rules of classical physics start breaking down, replaced by the strange logic of quantum mechanics, where particles can tunnel through barriers and exist in multiple states at once. Think of trying to squeeze a handful of ping pong balls into a shrinking box. At first, you can pack them closer together by reducing the empty space between them. But eventually, you reach a limit where the balls themselves start resisting further compression. They push back against the walls of the box with increasing force as you try to squeeze them smaller. Quantum particles behave similarly, but with an added twist as they get compressed into smaller and smaller volumes. Their quantum uncertainty actually increases their effective size. The more precisely you try to confine a particle's position, the more violent its quantum motion becomes. It's like trying to grab a slippery fish with increasingly tight hands. The harder you squeeze, the more frantically it struggles to escape. This creates what physicists call quantum pressure or degeneracy pressure. When matter reaches densities of about 10 to the 15th gram per cubic chem, quantum effects generate enormous outward pressure that can halt gravitational collapse. That's roughly the density of crushing every car on Earth into a space the size of a sugar cube. At such extreme densities, quantum mechanics essentially rebels against further compression. But even this quantum resistance might not be strong enough to stop the collapse of the most massive stars. When a star more than 20 times heavier than our Sun dies, its core contains so much matter that quantum pressure gets overwhelmed by gravity. The collapse continues beyond the point where normal quantum effects can stop it. However, this is where things get truly exotic. As matter approaches the density where singularities supposedly form, quantum mechanics might deploy its most powerful weapon, the breakdown of space and time themselves at incredibly tiny scales called the Planck length, roughly 10^35 meters. The smooth fabric of SpaceTime might dissolve into a thin foam of quantum fluctuations. Imagine zooming into what appears to be a calm lake surface. From far away, it looks perfectly smooth, But as you get closer, you start seeing ripples, then waves, then violent turbulence. At the quantum scale, spacetime might be similarly turbulent, with tiny bubbles of space and time constantly appearing and disappearing in a chaotic dance. This quantum foam might make it literally impossible for matter to collapse to a mathematical point. Instead of reaching infinite density, matter might encounter a fundamental graininess of reality itself. But there's an even more radical possibility lurking in the equations of quantum gravity. There might be a fundamental speed limit for collapse itself. We're familiar with the cosmic speed limit for motion. Nothing can travel faster than light through space, roughly 186,000 meters per second. This isn't just a technical limitation of our current technology. It's a fundamental feature of reality that even the most advanced alien civilization could never overcome. The universe simply doesn't allow faster than light travel.